What specific problem does the proposed Trajan method aim to solve in the context of evaluating video quality, and how does this relate to existing methods like FVD and pixel-based metrics?
The Trajan method aims to address the limitations of existing video quality evaluation metrics, particularly in capturing coherent motion across generated videos. Unlike the Frechet Video Distance (FVD), which is sensitive to frame-level content and relies on access to the training distribution, Trajan focuses on modeling 2D video motion through low-level, temporally extended motion features. This allows Trajan to evaluate both individual videos and distributions effectively, providing a more nuanced understanding of motion quality that is less dependent on semantic content. Additionally, while pixel-based metrics like PSNR and SSIM fail to account for temporal coherence, TRAJAN's reconstruction score is more predictive of human judgments regarding realism and motion consistency. Thus, Trajan offers a robust alternative that enhances the sensitivity to motion artifacts in video evaluations.
How does the proposed Trajan architecture work? Illustrate the step-by-step process from input point tracks to obtaining the latent representation and reconstruction scores.
The Trajan architecture processes input point tracks by first embedding the spatial and temporal coordinates of each track using sinusoidal embeddings, which are then projected into a fixed number of channels. Next, a readout token is added, and self-attention is applied to all tokens, utilizing an attention mask to account for occluded points. After this, the model retains only the readout token to create a fixed-length representation for each track. Trajan then employs a perceiver-style approach to cross-attend from a learned set of latent tokens to the track representations, followed by self-attention, resulting in a lower-dimensional representation of the tracks. Finally, the decoder reconstructs the tracks from this latent representation, allowing Trajan to compute reconstruction scores, which are indicative of the motion quality by measuring how accurately the model can predict the original input tracks.
Can you provide a simple yet illustrative example demonstrating how Trajan compares the motion features of a generated video with a real video? Please explain the steps involved in this comparison.
To compare the motion features of a generated video with a real video using Trajan, the process involves several key steps. First, Trajan utilizes the Bootstrapper model to extract low-level point tracks from both the generated and real videos, capturing the motion information. Next, these point tracks are encoded into a high-level latent representation using the Trajan architecture, which focuses on the motion rather than the appearance of the videos. Once the latent representations are obtained, Trajan computes the distance between the embeddings of the two videos, allowing for a direct comparison of their motion features. This method is particularly effective because it emphasizes motion consistency, enabling Trajan to detect differences in motion quality even when pixel-level metrics may suggest similarity. Overall, this approach highlights TRAJAN's ability to assess motion artifacts and inconsistencies in generated videos compared to real ones.
What are the theoretical or practical benefits offered by Trajan over traditional video evaluation methods? Specifically, discuss aspects such as sensitivity to motion inconsistencies and application in different evaluation settings.
Trajan offers significant theoretical and practical benefits over traditional video evaluation methods by directly modeling 2D video motion, which enhances its sensitivity to motion inconsistencies. Unlike conventional metrics such as FVD, which are biased towards frame-level content and do not effectively capture temporal coherence, Trajan utilizes point tracking to focus on motion quality independent of appearance. This allows Trajan to perform better in various evaluation settings, including distribution-level comparisons, pairwise video assessments, and individual video evaluations, where it consistently outperforms alternatives in detecting synthetic temporal distortions. Additionally, TRAJAN's reconstruction score correlates more strongly with human ratings of realism and motion consistency, indicating its effectiveness in predicting subjective quality. Overall, TRAJAN's ability to assess motion quality across different contexts makes it a versatile tool for evaluating generative video models.
How is Trajan validated or tested in terms of experimental design? What datasets, benchmarks, and metrics are used to demonstrate its effectiveness against other methods?
Trajan is validated through a comprehensive experimental design that includes comparisons across 3 scenarios: distribution-level comparisons, real versus generated video pairs, and per-video quality assessments. The datasets utilized for these evaluations include the UCF101 dataset for empirical video distributions and the EvalCrafter and VideoFi datasets for human ratings and physical consistency assessments, respectively. Trajan's effectiveness is demonstrated using metrics such as the Frechet distance for distribution comparisons, average Jaccard for reconstruction accuracy, and correlation with human judgments on aspects like temporal consistency and visual quality. Additionally, Trajan is benchmarked against alternative methods including FVD, VideoMay, and i3D, showing superior sensitivity to motion artifacts. The results indicate that Trajan consistently outperforms these alternatives, particularly in capturing motion quality and temporal coherence, validating its utility as a robust metric for evaluating generated videos.
What specific results and findings were achieved using Trajan in comparison to other video quality assessment methods? Please cite metrics or outcomes that illustrate TRAJAN's performance.
Trajan demonstrated superior performance in evaluating video quality compared to other methods across various scenarios. Specifically, it was found to be more sensitive to temporal distortions than traditional metrics like Frechet video distance, FVD, and appearance-based methods, as evidenced by its ability to detect synthetic temporal distortions effectively. In pairwise video comparisons, TRAJAN's embeddings captured motion similarities better than pixel-level metrics, which often failed to correlate with human judgments of realism and motion consistency. Additionally, TRAJAN's reconstruction score was predictive of human ratings for realism, appearance, and motion consistency, outperforming alternatives such as ClipScore and PSNR. Finally, in a detailed human study, Trajan consistently explained temporal and visual consistency better than other metrics, indicating its robustness in assessing motion quality across different datasets and models.